Takuya Kitagawa, the president of QuEra Computing. Today I want to talk about how we paved the way to fault-tolerant quantum computers. Just briefly, I'd like to introduce myself. I'm president of QuEra. My name is once again Takuya Kitagawa. At Harvard, cryogenic atom has been my research specialty. I worked for Rakuten Group for about 10 years as a senior managing director overseeing AI business. So I am currently running QuEra as president. So about QuEra, based on cold atom, we develop and produce quantum computers. Mission is to achieve scalable FT quantum computer that is useful to humanity so that we'll be able to accelerate innovation. Originally, Harvard, MIT professors created this company and university technologies are now being commercialized. The members are all related to Harvard and MIT. First generation quantum computer Aquila has been in use since 2022. So we already have a little less than 2 years experience. Quantum computer has been operated on top of cloud. You may have never seen this, so I have brought you this is the cold atom quantum computer. In the middle, you see the core of the computing. It's a magnetic coil inside. There is glass, quantum. That's where computation takes place. This coil will be frozen to trap the ions. And as you can see, they are sort of posing for the photo rotation. The founder and also Dorek, the Harvard student, they are looking at the optical table. All the qubit control has been done through laser, and this is the optical device to control the laser. And totally, you see we have 2 dining table size equipment. If you come to visit QuEra, you'll be able to actually see this box in person. Before I talk about fault-tolerant quantum computing, I'd like to introduce a computer that is already available in the market named Aquila. And this is analog quantum computer. And this is the only quantum machine that is available on cloud. 256 qubits are utilized. So this is the world's largest quantum computer available. Already many users are utilizing this for material simulation and optimization problems and also machine learning as well. Utilizing Aquila, the papers have already been written. So if you're interested, please search for those papers. Just one thing, just want to talk about the AI solution, quantum reservoir computing. This morning, Professor Yamamoto of Keio University talked about reservoir computing. This is the quantum machine learning solution. For several months on our machine, we have been able to implement this already for the very first time in the world. Quantum machine learning is truly available for the first time. So if you're interested, please use the solution. As Professor Yamamoto may have already explained, the concept is, first of all, there is input data and output answer. If the question is to recognize the host image in a neural network in the middle, they will actually take the correlation of the input information to be able to give the output, the answer. And right in the middle, we have quantum behavior, time evolution. By converting that to time evolution, we'll be able to create correlation quickly. So highly efficiently, we'll be able to implement and run the machine learning processing. Since this solution is available, our customers have loved this solution. Thanks to the AI boom, quantum computer has been accepted as one possible answer to do something that is interesting. So I want to talk about now fault-tolerant quantum computing, FTQC. You may not have to be preached, but recently, quantum computer, why is this necessary for the humanity? Simply put, quantum computers will change experimental science to computational science. Some of the science is developing very fast, other sciences are progressing slowly. Why is this? Chemical or biological sciences, when they discover something, they have to have experimentation. And excellent researchers will spend 10 years or 20 years consuming 10 to 20 million yen to be able to discover something. For example, drug discovery. Even without experimentation, if you can discover with only computation, this will accelerate scientific evolution itself. The overall advancement of science can be as quickly as 10,000 times or maybe 1,000,000 times faster. If you are going to convert CO2 into methanol before the combustion, if we can find a catalyst, we will be able to save the humanity, for example. Having said that, quantum computer has never experienced the Industrial Revolution. So the major issue that we recognize is the error rate. In the world, the best possible quantum computer, even with this great computer, has 0.1%. It's always exceeding this error rate. So meaning that you have to do 1,000 calculations. So revolutionary computation requires 1 trillion to 100 trillion cases of calculation. So we need many more digits calculation improvement. In order to go over 1 digit improvement, it takes 3 to 5 years in the past. So roughly speaking, you may think that it may take 30 or 50 years to get to that fault tolerance level. But this problem has been known for many years, and many solutions are proposed. And one of them is the error correction technology for quantum. This is, for example, alluded to 5G. This is classic error correction technology. Think of a communication channel. When there is frequent error, I would say, I am going to send 0 or 1 bit. If I'm sending 0 along, when there is a mistake, what I'm sending is going to be 1. On the other hand, if I keep sending 0, 0, 0, and there may be one of those zeros replaced with 1 by mistake, but basically you know what I'm saying. I'm sending 0. And that principle will be applied to quantum error correction. And as you can see, quantum error correction technology, to realize this, we need 2 things. One is physical qubits. We should be able to generate many of these. And the other one is for each qubit, the physical error rate must be contained to a low level. And we have to achieve both of these requirements at the same time. For the past 15 years, quantum users, many companies have tried to overcome these problems at the same time. And it has been a major challenge. But there has been a major change, a breakthrough last year. Our Harvard QuEra group finally achieved 48 logical quantum qubits. And this has been announced in the Nature. Other companies are also working on this, but they have only 1 digit logical qubits. So what we've achieved is the highest number of logical qubits, and that is why we have caught a lot of attention from possible customers. So I'd like to show you how it looks like 48 logical qubits, how they are calculated. I have this animation. Each one of these green dots is an atom in our system. It represents a qubit. As you can see, optical tweezer, the laser technology is utilized to move them. So those circles are actually pulse that are controlled. As you can see in this video, there are two characteristics. One is the fact that qubits, atoms, all you have to do is to lay those atoms, and then you'll be able to increase the number of qubits. Thanks to that, we have close to 100 to 200 qubits here. So several thousand qubits can be laid out, as you can see. The other characteristic is that you can see all of these qubits are moving at the same time. In other words, concurrent calculation is possible. You can move qubits at the same time, meaning concurrent calculation is possible. Logical qubits are necessary for calculation for the next generation problems and applications. A physical qubit has higher overhead. Overhead tend to get increased rapidly, but with logical qubits, we will be able to contain the level of overhead of calculation. And there are multiple platforms. Many companies are working on them. There are much larger companies working on this. Why QuEra is trying to scale this FTQC. You may just wonder why we're working on this. Just want to explain the reasons why we are working on quantum error correction. As I said, just laying qubits is possible to increase the number of qubits. So thousands of qubits can be realized easily. As you can see in the second box, increasing the number of qubits and error rate reduction. It's often the case that they are trade-offs. In some of the platforms, if you increase the number of qubits, you tend to have higher error rates. For the past 15 years, because of that, it was very difficult to achieve error correction. But as you can see here, we have a place where you can place memory, and there is a place where you do the computation. They are separated. So it doesn't matter how much you increase the number of qubits, it's not going to impact the error rate. Error rate is not going to be impacted by increasing qubits. Overwhelmingly, this is favorable for achieving scaled logical qubits. And concurrent operation, as I said earlier, if you saw the video, you see, you get the hunch that this is good for a concurrent operation. According to our calculation, 1 digit to 2 digit tend to 100 times more computation is possible with the same level of quantum circuits. Sorry, I was moving too quickly, but these are the technologies that we have in our companies. We have already announced this public roadmap. This is logical qubits, the level of logical qubits that we want to achieve. Eventually, in 2026, before that, 100 logical qubits, we want to achieve this number by that timing. And this roadmap, compared to other companies, is extremely aggressive. As I've explained, we have technologies, and these technologies are evolving. We are moving positively toward this goal. Although this is ambitious roadmap, we will be able to contribute to quantum computing community in the whole world. We would be able to become the next generation NVIDIA in quantum world. So we have several ways of providing quantum computers. One possible way is to introduce the hardware itself to companies or research institutes, have them directly use the hardware we provide. The other way of delivering our solution is not providing hardware, but on top of cloud, we would like to make sure our solutions are available to our customers. Already, other solutions have been, we are negotiating with other companies to be able to integrate other companies' solutions as well. And in a limited way, our quantum computer can be utilized to develop killer applications. In order to expand our market, we have to be able to provide solutions that are good for different industries. Once again, this is our development jointly done with a limited number of partners. Using this quantum computer, we would like to jointly develop killer applications that will solve specific problems to certain industries. So first of all, in terms of providing hardwares, I'd like to introduce what is already decided, especially in Japan. AIST has ABCIQ supercomputing facility where they've already decided to use our hardware. NVIDIA GPU along with our hardware will be installed next year. It could be used as standalone. It could be also used in a hybrid manner. Since they are physically close to other Japanese companies, if you're interested in creating killer applications using quantum computers, please do make use of this facility. Our booth is set up in the adjacent room, so please come visit us. Outside the country, outside Japan, UK, we already have the testbed introduction decided. QuEra, the UK Computing Center, is going to introduce our hardware-based testbed. So with that, last year we had a major inflection point, and physical qubit to logical qubit is a shift that we are leading, and we believe that we are a frontier in this transformation. Along with AIST adoption of our hardware, we have already decided to set up a subsidiary in Japan. Especially if you're interested, if you're an expert in cold atoms, please come talk to us. Thank you.
北川さん、ありがとうございます。
Thank you. We have several questions. Kitagawa. The lasers are available. How many atoms can you trap with available lasers? And this is something that you should look forward to. There will be so many ions that we'll be able to trap. On top of your quantum computer, what are the applications that can utilize your advantage most quickly? This is a very good question. I would like to know your opinions, but there are several promising applications that we are exploring. Naturally, material development would be one, and Welcome Leap is a program that we are promoting for biology and medical applications. We are trying to establish this application as well. We're hoping to find a major killer application. Since we are a hardware vendor, we have excellent application developers. We have a very good group But we believe that the application should be discovered in a community so that the application should run on our hardware. So we are always open to possible collaborations. And there is another question. The qubit layout limit, is it possible to the size of atom level? The limit of laying out atoms. Realistically speaking, we have to avoid crosstalk between these bits. So you won't be able to achieve atom level. Based on that, you think of the diffraction limit of the laser itself. That would be the limit of atom layout. Thank you very much.